This webcast talks about how to write equations of motion for things that are moving at a constant velocity. So the equation of motion is the equation that describes how the position of the object changes as the elapsed time changes. Those are the two variables. This equation is really the physics equation that you would see for a position versus time graph. And just as an example, here is one of that type of equation where we have x, that's the dependent variable, x means position, x equals, in parentheses, we have the slope, which is telling us the velocity. So in my example, that's 3 meters per second. That velocity is multiplied by delta t. Delta t is the independent variable. That means the elapsed time, plus 4 meters. In this case, 4 meters would be the initial position, or the y-intercept of the position versus time graph. So when you write an equation of motion, you are only filling in the velocity and the initial position. You will leave x and delta t as variables for this equation. Here's an example where we have two trains, and so we've got a position versus time graph. As I'm looking at this, I can see that the blue line, that's for train A, has a positive slope. So train A must be moving in a positive direction. And then the orange line, which represents train B, has a negative slope. So train B is moving in a negative direction. They do not start at the same place. Looking at the y-intercepts, I can see that train A begins at position 4 meters and train B begins at position 80 meters. So the two equations of motion are shown here in the bottom left side of the screen. And I just want to call your attention to the fact that for train A, I was told that it's moving in a positive direction at 4 meters per second. And so I want to make sure that in its equation of motion, the velocity is a positive 4 meters per second. Also, they told me that a train A started at position 4 meters, and so 4 meters is the y-intercept of this equation. Now, train B is moving in the negative direction, and so it's important that the velocity of train B be negative, because the slope must be negative if the object is moving in the negative direction. Okay, let's look at one more example here. Sometimes it is a good idea to find the time and the position where two objects pass each other. Or this could be where two objects are crashing into each other. So you would certainly want to know that. And so I'm just continuing with this example of the two trains. So I'm looking for the position where they either pass or crash into each other. That would be this, where this yellow square is now. That's the intersection of their two position versus time graphs. So the process for doing this, first I need to write equations of motion for both objects. I have to be careful that the time frame is the same for both objects. In other words, when I put in the initial position at time 0 in my equation of motion, I have to be assuming that the time zeros are the same for both objects, okay? That only becomes complicated if one of the objects may have a head start. But anyway, in this case they don't. And then we want to set the two equations equal to each other, and we want to solve for time. And then we will plug that value of time that we found back into both equations to find the position. And so here's an example of that. So I've got the two equations of motion, which we discussed in the previous slide. I set them equal because because I'm looking for the point where they are at the same position. X is the same for both trains at that yellow box. So I set the equations equal. I get all of the terms that have the delta t variable on one side of the equation and everything else on the other side. And so I can solve for delta t. And in this example, I find that it's 6.91 seconds. Then I take that value of delta t and I plug it back into both equations. And I find that at time 6.91 seconds, both trains will be at a position of 31.64 meters.